All right. So you guys have seen a hydrate before. I've mentioned it before, but we never really described what it is. So what a hydrate is an ionic compound. And remember how ionic compounds typically look, right? It's a lattice of ions, and they're alternating. The positives are next to positives, the negatives are next to negatives, right? That way everything attracts. When these ionic compounds form, often they're formed in the presence of water, and eventually the water leaves and dries out, and that's what leaves the solid crystal. So ionic compounds often have little bits of water trapped inside. And right, as a solid, like these are crystal granules, they don't look like they have water in them, but they do. They're just trapped and they can't leave. So that's what's called a hydrate. It retains water that's trapped inside. Now, hydrates can be dehydrated simply by heating them. So if I took a solid sample of an ionic compound that I knew contained water and I heated it, let's shrink that down. Why won't you shrink? All right. Anyways, if I heated it, let's say we put it in a crucible, right? And you have the flames underneath it. All of these ions start to vibrate and shake, right? Because these atoms and these ions in place, the more you heat them, the more they vibrate. And the more they vibrate, then the wider these gaps get. And then the water leaves. It just evaporates out. It leaves. And eventually what you have at the end is just the solid with no water left, right? It's all gone. We have a term for this. When all the salt is gone, this is what we call the anhydrous salt. An means without, hydrous refers to water, and ionic compounds are often called salts. Whereas over here at the start, this is what we call the hydrate, which includes the water. Okay, so hydrates are ionic compounds. They have water trapped in between ions. We heat it, and the water is forced out. Okay. We can tell this is happening because we can weigh these before we heat them and after we heat them. And there'll be a mass decrease, right? Because the water had left. So that's some matter that has left. Now, there's a mathematical ratio to the water and the compound, and that's what we're going to calculate in our lab, in our next lab. So the compound of a hydrate looks like this. It has a salt, and it has water, and it has some kind of integer. Okay, so the integer here, this ratio is a whole number. In this particular case, they're showing 5, but it could be 2, it could be 7, it could be 1, it could be whatever it is for that particular compound. And the goal is to figure out what number that is. So we're trying to find the mathematical ratio between moles of the compound and moles of water. So here's how we do this. This process is it's very, very similar to empirical formulas. Okay, and that your first step is to find moles. So let's say we had 1 gram sample at the beginning. So 1 gram sample, and it's barium chloride, and it's a hydrate. It's got some water in there. We're trying to figure out what that number X is. So we heat it, and the resulting substance weighs 0.8574. So this is the total mass, total at the beginning. This is the end. Okay, and hydrates, they lose mass because water leaves. So the first thing we need to do is find the mass of water that left. So we subtract 1 minus 0.8574. So we get 0.1426 grams of water. Let's convert that to moles. And we get 0.00791 moles water. Okay. Just like in an empirical formula, we need moles of both the water and the salt. So I have the moles of the water. I need to figure out the moles of the salt. And we know how much salt there is because they told us. It was 0.8574 grams of BaCl2, because that's what remained after we heated the hydrate. So let's convert that to moles. So if we need to find the molar mass of barium chloride, let's add that up real quick. 137.3 plus 2 times 35.45. So this is 208.2 grams. And so this is 0.004118 moles. All right. I have my moles of my anhydrous salt. I have my moles of the water. I'm trying to find a ratio. Just like with empirical formulas, if you're trying to find a ratio, you divide both numbers by the smallest number, which is 0.004. That, of course, will be 1, and this is looking like it's going to be 2. 1.92, which is basically 2. Hydrate values will be integers. 1.92, you can round that safely to 2. So what that means then is your formula, their value of x is 2, so your formula is going to be BaCl2.2H2O. And this little dot right here is not multiplication. It's just how we write the formula of a hydrate. It's just like saying there's 2 waters attached. Think of it more of like a plus sign. Okay. All right. So this is your typical hydrate problem. Find moles of both parts. There's 2 parts of a hydrate. There is the salt, there's the water. You need moles of both parts, and then you need to divide both by whichever one is smaller. That's how you get your value of x, and that's how you write your formula. Okay. So let's try another example. Borax is one of the original laundry detergents. It comes in flakes in a cardboard box before they use liquid detergents for your washing machines at home. So it's also a hydrate, right? So our hydrate mass is 1 gram. We heat it. The anhydrous salt weighs 0.527 grams. Remember, anhydrous means after heating. After heating without water. Okay, so let's figure out our masses for both parts. So 1 gram hydrate minus 0.527 grams of Na2B4O7. Okay, I've got my masses of both parts. So let's find moles of the salt first. 0.527 grams. A mole of Na2B4O7 weighs see, boron is what, 10.7? 10.8. Okay, 201.24 grams. 0.00262 moles of that compound. All right, let's do water next. All right, we got 0.0264 moles of water. We got moles of both parts. Next step. What do I do next? Nisha, what do I do next? Divide what? Divide moles by moles of what? Right. Divide them both by the number that's smaller. Okay, so this will be 1, this will be 10. So our formula for our hydrate is Na2B4O7.10H2O. How are we doing? It's not too bad after having already done empirical formulas and molecular formulas, right? It's just like another form of an empirical formula problem, okay? The key thing to remember is that when we say hydrate, hydrate is the whole thing, right? This Na2B4O7 is the anhydrous salt. It's just the ionic compound without the water, right? But this plus this, of course, have to add up to what the total is. Okay. So let's take a couple minutes and have you guys do this one and see if you come up with the same thing that I do. The molar mass of beryllium sulfate is 105.08 grams per mole. Let's put that up there to save you some time. All right, so here's our general setup. You're starting with a crucible. This how much away is empty. This is your crucible with the hydrate there, which the label has gone away. And then this is your crucible after it's been heated and dehydrated. So your mass of the crucible with the hydrate, your mass of the crucible after heating should have gone down. So 25.254 becomes 24.230. Okay, so sometimes drawing out a diagram helps you make sense. We need to find masses. So the masses we need are the grams of the water and the grams of the anhydrous salt. So if you look and see what the numbers are that they gave you, I can take this mass, subtract it from this mass, because the difference between these two is the water. So in doing that, I get a mass of 1.024. So 1.024 allows me to solve for my moles of water, which is 0.0568. I need the mass of the anhydrous salt, so I can do that by subtracting the end mass, because here in this crucible is just the crucible and the salt and the crucible. Subtracting these two gives me 1.46. So 1.46 grams of the beryllium sulfate, which is the anhydrous salt. The number of moles I get is 0.0139. So at this point, when you have moles of both, just like an empirical formula, divide them both by the number that's smaller, 0.0139. We get 1 and 4. So your formula will be BeSO4.4H2O. How did we do? Did you guys get that? Yeah? Okay. So that's hydrates. Okay.